Hello, college algebra. So here we are with inverse functions again. This time we're going to prove it with the definition, okay? So now what we've talked about before is all it is to be an inverse function is to switch the x and the y variable, right? What we're going to say here is then if we by the definition, if we have an f of x here, and we know that what that function is, then what we can do if this is the y, right? This is the y, then the inverse of f, the inverse, that's what that notation is, would just be the opposite of that, right? Where we're just going to take the y and it's going to equal the x instead, right? So there's the definition that we're working with. We're just literally switching the f and the y around, and that's what it's going to look like. So let's see it work on, again, an example that we know to be true because we've been using this as an inverse operation. So we know these two are inverse functions. So let's just see. So here's how you do it. So like you take this first one. Well, we know f of x is just another representation of the letter y, right? So that's what this really is. So what we can do then is we can say, hey, if this is what f looks like, well, we can just switch the x and the y around to see if it's going to look like the h. So now, of course, we got to solve for y because the problem is y is what we want to make it equal because that's how you name a function is with the y, right? So now that we've switched the variables, that's the definition of inverse functions. We need to solve it back for y. Looks like we need to do an inverse operation right here to get the y back into the playing field. That inverse operation is taking the same base log, right, of the left side. If I do it to the right side, we know that that's going to eliminate that to give us y. So then what we have is a new function. This new function is the inverse of f because that's what we did. We built it. So then we look, and this is the inverse of f, and we see that it does match that. And since it does match h, we can answer this question with yes, these are inverse functions because h is the same exact function as f inverse. Okay, so let's see it again over here. I'll go purple because it's Easter and I'm doing this. So we got q is this, right? So instead of q, we're going to say, hey, we don't want to call that q. Let's call it y instead. Because we know it's just a function. Using the definition of inverse functions, we're just going to switch that y and x around and start solving for y. Get y alone. So add 2 to both sides. Then we're going to divide by 3. So we're going to get y is equal to 1/3 x divided by 3, plus 2/3. Distribute that division. This then is the inverse of q by definition. Since it looks the same as this function, we say that j and q are inverse functions. So just like before, when we're answering the question of inverse functions, it's always yes they are or no they're not, 50-50, right? But the real proof is in the pudding. You need to prove this mathematically. So now you have two ways you can do it. Composition of functions, or you can use this definition where you flip-flop the x and the y. But you have to prove that two functions are or are not inverses. Remember, if this didn't look like this one, then the answer is no, and the proof is already done, right? If this right side didn't look like j, then we would not have inverse functions, okay? Email me if you have any issues.